Welcome to the lecture on deep learning in artificial neural networks. We continue our discussion of the statistical interpretation of artificial neural networks and ask the question, can we interpret the output as a probability? We have seen previously that the interpretation of the output as a probability suggests that we should choose the cross-entropy error function and minimize this one. Now, suppose we do that. Suppose we minimize the cross-entropy error function. Can we then be sure that the output y hat will represent the probabilities? Well, somehow, no, because we will need additional assumptions. First, we will need enough data for training. If you only have 10 data points for a complex task, it's not going to work. We know that. And then we also need a sufficiently flexible network. If you use a simple perceptron without any hidden layers for XOR task, we know that it's not going to work. So we do need additional assumptions. So suppose we minimize this cross-entropy error function. And now let's assume two things. First, we have enough data for training. And second, we have a sufficiently flexible network. And then we try to find out whether we can get from cross-entropy loss function to output probabilities. The assumptions will become more clear during the discussion of the argument. So let's start. So here's our cross-entropy error function, and we have the sum over all patterns. And if t mu is +1, then this term contributes. If t mu is 0, then the other term contributes. Let us therefore split this sum in its two components. I have x mu that are part of the class, in which case I have the logarithm y hat mu, and then I have terms where x mu is a counterexample, it's not part of the class, in which case I have the term 1 minus y hat mu. And now we exploit our two hypotheses. The first one is hypothesis A. We have many examples. So I've started here a little plot. Suppose we are in one dimension, the input is just x, and then we have our outputs. The outputs would be the targets, and we are in a classification task, so the targets are either 1 or 0. And now we have many examples. So at each location we have many positive examples, maybe like this, and we also have many negative examples. Okay, so now the idea is that for each little segment, suppose I have a segment here, this is a certain bin, and I call this my bin XM. So we have several of these bins. And now the assumption of many examples means I have many positive examples in that bin, and I also have many negative examples in that bin. So let's look at the number of positive examples in that bin XM, and I call this N1 of XM. And well, imagine we have lots of examples. So how many of these examples would we see then? Well, it would just be P of x c times delta x. So this is the probability density of having class C, which means the label T mu equal +1, and an input value x. Now, similarly, the number of negative examples in the same bin xm would be n0 of xm, and that's just the probability density that I have non-class members, I denote this by the bar, in region x, and the actual number will depend on this delta x, which is my discretization. So delta x is a typical bin size. So this now allows me to rewrite the loss that we have up here in terms of a sum over the bins. So my error or my loss is still a function of W. And now I say, well, I have this sum over all patterns, but the sum over all patterns is the sum now over all bins, each of these little bins. I sum over the bins, and then in this bin xm, I have a certain number of positive examples, n1 of xm, and for this number of positive examples, I take my logarithm y hat of xm. The whole thing comes with a negative sign. And now I continue the sum, and now look at the negative examples. In that same bin, I will have n0 of xm negative examples, and for these I take the other term, and so I take logarithm of 1 minus y hat of xm. Note that previously here in this line it was a sum over the patterns, and now we say it's a sum over bins, and in each bin I have a certain number of patterns. But then of course the output at this bin only depends on the x value. It cannot have different outputs. So it's always the same output y hat at this location xm. So this is the strength of the first hypothesis, hypothesis A. I have many examples, and so in each bin, in each of these bins, I still have many examples. Now let's look at the second hypothesis. Second hypothesis, the network is flexible enough. So flexible enough. Well, I want the network to be able to say, in this bin here, I want a very low value, but in the neighboring bin, I actually want a very high value. So the network must be super flexible that it can jump up and down as it must. And we still work in this bin-wise description. The network is flexible enough. That means in each bin, the output y hat of xm is arbitrary. And that means I can directly optimize. So I can optimize and I'll say, well, this y hat of xm is a free parameter. And in this bin, it can have this value. In this bin, it can have that value. In this bin here, it may take this value and so forth. So in each bin, it's an independent value. So let's optimize. And that means I can take the derivative of this loss with respect to this value y hat of xm. So one of these free values, these are now my free output variables. We are flexible, the output is completely free, and I want to find the best position. Now let's take this derivative. Let's take this derivative in the first term. Well, I take the derivative with respect to one of the y hats, the one at xm. So it's only the relevant m that matters. The sum goes away. And now for this bin that I'm now working, say this bin here, I take the derivative with respect to this. So this goes in the denominator, y hat of xm. And in the numerator, I have the factor in front, which is n1 of xm. And then I have my second term. Same thing. I take the derivative with respect to y hat. This will give me a minus sign. 1 minus y hat of xm. And then, well, it's just the other factor, n0 of xm. And now we can multiply out, and for example, we can multiply out with this term, and we can multiply out with that term. And so what we have is 0 equals n1 of xm times 1 minus y hat of xm minus n0 of xm times y hat of xm. And now we can solve for y hat. Y hat at this arbitrary bin xm is then n1 of xm divided by n0 of xm plus n1. Okay. Now let's go back to our definitions here. N1 is just a probability. N0 is the other probability. So if we plug this in, then what this gives is that these ideal output lines have a value y hat which is just the ratio n1 at this location divided by n0 plus n1 at the same location. And the location is always, say, now bin k, so I put here k, x, k, x, k. And well, what is this? If you plug in our definitions, then this is P of C given xk. So with these two assumptions, assumption A, assumption B, what we find is that the ideal output just reflects the relative number of data points, and that means it reflects the probability that given xk we have C plus C given xk, but that's exactly what we want. We wanted that the output can be interpreted as a probability. So let's summarize. We used two assumptions. The first one, we have many, many examples. The second one, our network is flexible, flexible, flexible. It can do whatever we need. Then if we minimize the cross-entropy error function, then we find an output that can indeed be interpreted as the probability that the data point x belongs to the class. And this is valid for an arbitrary data point x. Two notes. The first one is, you see from the proof that the flexibility must somehow match the number of examples at x. I need lots of examples, and then in each small bin, I still need lots of examples. But the bin size that I chose somehow reflects a regularization, reflects an intrinsic flexibility of the network. And the second comment is, well, for this kind of proof, where you have data n0 and n1 at location x, think of high dimensions. You would need lots and lots and lots of data. Let's finish with a little quiz. We covered quite a bit of ground, so let's talk about the first three options first. Maximum likelihood solution means find the unique set of parameters that generated the data, or find the set of parameters that best explains the data, or find the best set of parameters such that your model could have generated the data. And it's not an exclusive or. So what are your choices? The second and third options are correct. Now let's look at the second question. Minimization of the cross-entropy error function for single class output is consistent with the idea that the output y hat 1 of your network can be interpreted as the probability that input x, given input x, the probability that it belongs to the class C. And stronger, is that also true? It guarantees that the output y hat of your network can be interpreted as a probability. And here only the first option is correct. As we have seen, for the second option, you need quite a bit of very strong additional assumptions.